Hey everyone, so my name is Zach Vines, and what we're going to go over today is how to solve a one-sample hypothesis test based on p-value. So first of all, I wanted to map out sort of beginning to end what's going on at a high level here, because when we're dealing with hypothesis testing, especially if we're going to solve with it using a p-value, there's so many different ways that you can do this problem based on the exact situation at hand, whether or not it's a mean-based problem or a proportion-based problem or how large or small our sample is. It's just sort of various assumptions that affect things throughout the process. So this is going to be just a high-level overview of the process. We'll drill down into a couple of details and give you two examples on the tail end to sort of wrap everything up. So to start off with, when you're solving for a one-sample hypothesis test and you're using the p-value to solve for it, the first thing you want to always set up is what's called your three-number summary, where it's simply going to be n, which is the number of trials in your sample, however many things you're sampling for that particular sample, either an x-bar if you're dealing with a mean-based problem, meaning it's the sample mean, that's your x-bar, or f, which is going to be your sample proportion if you're dealing with a proportion instead of a mean. So sometimes I've seen f being called p. Long story short, make sure this is just the sample proportion information, whichever variable you're supposed to call it for your particular class. And then finally, your standard error, which again, you can solve for in a couple of different ways. We'll get to those details in just a moment, but you want to list out your n, your x bar, f, and your standard error to start off with. Next, you have to set up your hypothesis. So I actually made a video recently, and I'll put the link in the description on that and timestamp it for you so you can reference that. But essentially, you set up your hypothesis. So if it's a two-tailed test, you say either mu or pi, so mu being your mean of your population, and pi being the proportion of your population. Again, sometimes I've seen pi represented by a different variable, but it's going to be the population proportion is what you put in the hypothesis. Always put in population information in the hypothesis. If it's a two-tailed test, you're saying mu or pi, whichever one you're using, is equal to a certain number or it is not equal to a certain number. Whereas a one-tailed test, you say either greater than or less than or equal to that number, and then just flip that logic right there. And again, I have another video that goes into a lot of detail on how to decide how to set that up, so definitely check that out if you haven't yet. Finally, we're going to do the setup, the test statistics, so the z or t value, and solve for it. So whether or not you know it's z versus t and exactly how you find that value is going to be different between situations. The next set that we'll go into is actually kind of drilling down everything that goes into step 3. So just sort of lock that in for right now, and we'll go into the details in just a moment. After you find your z or t test statistic, you're just going to either one of two things. If you're having to use the z or t tables to find a p-value, then I have another video that I'll put in timestamp and put in the description of how to read those z or t tables to find your p-value. Or if you're going to solve for it with Excel, which again I'll have another video for on how to solve with it to find the p-value in Excel, you solve for it for there to find your p-value. Finally, once you have your p-value, you're going to compare it to something called alpha, which is known as a level of significance. And essentially, the phrase I like to tell students that seems to help out a lot is if the p is low, reject the HO. The HO, the null hypothesis, what were you thinking about? Anyways, let's go into this step 3 right here, talk about what all goes into that, and then we'll segue into a couple of problems. Okay, so now what we're doing is drilling down step 3 from those series of 5 steps we just went over, talking about how to set up your test statistic, either your z or t value, and how to solve for it. So essentially there are two different benchmarks I've seen in a couple of different classes as far as what decides if it's a z or a t test. Make sure based on whatever class you have that you're looking at the associated benchmark, because I've seen one method where we're dealing with n and one method where we're dealing with whether or not we know the population standard deviation. Most of the time this should overlap and give you the same thing either way. But just make sure that whatever benchmark you're using for your particular class is the one you focus on here. But the two methods you use to decide between z or t, one of them is based on n. So essentially, if n, the number of trials in your sample, or the number in your sample essentially, is greater than or equal to 30, meaning it is 30 or greater, then you're going to use a z-test. On the other hand, if n is less than 30, then you use a t-test. So that's one way to do it. Another way to do it I've seen is that if you know the population standard deviation of the problem, it just gives you that information, then you're going to use a z-test. If you do not know it, then it's going to be a t-test. And finally, if it's just a proportion-based problem in general, like we're not dealing with a mean or an average, but it's a part out of a whole or a proportion that we're interested in, we just jump straight to a z-test, okay? So to actually solve for those, it's the same formula for every single one of them. For z or t, this is how you solve for the z or t. It's going to be the same number when you solve for it right here, but the way you use that number afterwards is what ends up giving you a different answer. So it seems kind of weird we're deciding between z or t, yet it's the same formula, but you'll see after we go through an example, the steps you take after that are going to be different even though it's based on the same number. So just keep that in mind. But essentially for the formulas for your standard error, or I'm sorry, for your Z or T test statistic, the base formula for it is just whatever you have for your sample minus whatever you have for your population divided by your standard error. And I know whatever you have is a really generic term because it's kind of hard to equate the two. Here's what I mean. If it is a mean-based problem, you are taking your sample mean, so sample, minus your population mean, mu, and dividing it by the standard error formula for a mean-based problem. So if you have a mean-based problem, this is the formula you use to solve for Z or T. So it's x bar, the sample, minus mu, the population, divided by its specific standard error formula. Whereas with a proportion problem, instead of x bar, we're using f, which we just said a moment ago is the sample proportion. So it's still the sample-based information, but the proportion instead of the mean, because it's a proportion problem, not a mean problem. And then pi right here represents the population proportion. Again, I have seen different variables used for different, especially the proportion variables here. So just make sure you're taking the sample proportion minus the population proportion, whatever variables are used. These are the ones that I'm comfortable holding on to, and divide it by this big number, which is how you solve for the standard error for a proportion problem. So both of these denominators give you the standard error, but depending on whether it's a mean problem or a proportion problem, decides which formula solves for the standard error. So just plug into pi times 1 minus pi divided by n, square root of that whole thing. And keep in mind that pi is the population proportion right here. So make sure you have all that written down. Again, this is all very high level to start off with, but we're going to run through 2 examples right now, give you kind of a ground up overview on how to go through these problems, and we'll take it away. All right, so now we're going to go through an example, and I'm going to have this entire example listed out in the description, so I have it right in front of me now, but just make sure to check out the description. It gives you all the details I'm about to read. Everything's worked out, but let's just go through it from beginning to end. So what we have here is a simple random sample of 300 items is selected from a large shipment, and testing reveals that 4% of the sampled items are defective. So the supplier claims that no more than 2% of the items in the shipment are defective. So we have to carry out an appropriate hypothesis test and comment on the credibility of the supplier's claim. So we're just going to go through those first 5 steps like we just went over in the very beginning of the video from beginning to end. So to start off with, we need to do our 3-number summary. So as far as n goes, there was a sample of 300 items that were selected. We sampled 300 items, so n must be 300. As far as a proportion goes, we know we're dealing with a proportion-based problem here, not a mean-based problem, because everything they give us is talking about a percent of the items that are defective, not a particular number of them, like an average amount that's typically defective. It's a percent of the whole that is. So we're clearly dealing with a proportion-based problem. They say that in that sample, 4% of the sampled items are defective, so f, the sample proportion, is going to be 0.04. And then to find the standard error, what we talked about from before, it's that big square root pi times 1 minus pi divided by n. Now that pi is going to be the population proportion, and we're actually going to find that in just a second, so just sort of hold on to that formula. Now when we set up our hypothesis, the way we set it up, and again, I have another video that really goes into the fine details on how you can decide the direction of the inequality. We know, first of all, that this is going to be a one-tailed test, because in a one-tailed test, we're considering one direction only. We're not saying it is this number or anything else. We're saying it's a particular relationship, either greater than or less than this certain number. And what we're talking about here is assessing the supplier's claim that no more than 2% of the items in the shipment are defective. So he's talking about specifically 2% or less, no more than 2%. That's certainly one-tailed. So the way I would set it up, and just again, the other video will explain plenty of the nuance that goes into this. But long story short, I'm trying to exclude my sample proportion from my null hypothesis. My sample proportion is 0.04. So if I want to exclude that from my null hypothesis, I would then say that pi is less than or equal to 0.02, because that doesn't include the 0.04. If I said greater than, it would include the 0.04. Don't want to do that, so we set it up just like that, flip it around for the alternative hypothesis. So that's how you set up the hypotheses. So considering we're hypothesizing about 0.02 being the population number, 0.02 is what we put in for pi. So square root 0.02 times 1 minus 0.02, which is 0.98, divided by 300, big square root around that, gives you 0.008. And then finally, it doesn't necessarily tell us a level of significance or an alpha value. the rule of thumb is if they don't give you a specific level of significance, assume 0.05. So in this case, they didn't, so I'm just going to say alpha over there is 0.05. So from there, we're just going to solve for our test statistic. So asking whether or not it's a z or a t. In this situation, we're just going to use the either n being greater than or less than 30 as our benchmark for that. And it's also a proportion-based problem, so you know it would be z either way because n is greater than 30, and it's a proportion-based problem. So we're going to jump right into that z. Whichever threshold you use to decide between the two is going to decide z right there. So as we solve for it, it's just f minus pi divided by the standard error. So we took the f value that we listed out in the beginning, subtracted out the pi value we have right there, which is just the sample minus the population, divide that by the standard error that we solved for up on the left side, so we don't even have to do that calculation. Solve for all that, you get a 2.50 z value. Now, depending on whether or not you have to use the z-table or Excel is going to decide how you go about this part right here to find your p-value, but both of them are going to give you the same answer. So if you use your z-table, it's going to end up being 0.0062, and again, link in the description shows you exactly how to read the z-table, very short video, very simple explanation. For Excel, we have another video for that where I have a chart basically drilling down the steps that you need to go through to decide which Excel function to use. In this situation, because we had a z-test, our alternative hypothesis indicated a one-sided upper tail test, hence the greater than in the alternative hypothesis, means that we're going to use this Excel function right here. So again, you have to watch those videos in order to understand the logic between these. They're very short though, I'd recommend watching them, it'll clear a lot up. So right here, we're going to use equals norm.dist, plug in the zc, which is just the z value we calculated, comma 1. And when you punch that in, the p-value you get in either method is 0.0062. So finally, we're going to compare that p-value to our alpha. And you remember the rule, if the p is low, reject the hoe. So we have p-value is 0.0062, alpha is 0.05. That's certainly less than alpha. So we are going to reject the null hypothesis. And the last thing we really need to do is to kind of bring this into real life terms. Like, okay, we're rejecting HO, but what does that actually mean in the context of the problem? Well, we're rejecting HO, meaning that we're failing to reject or we're accepting HA. What HA says is that the population number, the population proportion of defects is actually going to be something greater than 2%. So the supplier's claim is that no more than 2% of the items would be defective. So we're rejecting that, which is what the null hypothesis would be, and we're accepting the fact that the number of defects is actually greater than 0.02, meaning that the supplier's claim is not credible. So let's run through one more quick example to sort of wrap everything up. All right, so one final example to go through. Again, the whole problem's listed in the description, so read along with that as we go through it. So what we're looking at is that it's been reported that the average life for halogen light bulbs is 4,000 hours. So that's what's reported. Learning of this figure, a plant manager would like to find out whether the vibration and temperature conditions that the facility's bulbs encounter might be having an adverse effect on the service life of bulbs in her plant. In a test involving 15 halogen bulbs installed in various locations around the plant, she finds that the average life for the bulbs is 3882 hours with a standard deviation of 200 hours, assuming the population is normally distributed using 0.25 level of significance. Do they tend to support the manager's suspicion that adverse conditions might be detrimental to the operating lifespan of halogen light bulbs used in her plant? That's a mouthful. Let's just go through the steps how we did before. So to start off with, we need our three-number summary where we have N is going to be the number in the sample, the number of trials. Here, if you kind of read all the way down, we have that we did a test involving 15 halogen bulbs installed throughout the facility. So those are the things we're testing are the light bulbs. We tested 15 of them, N is 15. Then in the sample, what was the mean life of those light bulbs? We can see that the average life for the bulbs in the sample was 3,882 hours. So we put 3,882 for our X bar. Then we have to solve for our standard error. Now remember, if we have this type of problem here, where it's a mean-based problem, not a proportion-based problem, the way you solve for your standard error is just S, your standard deviation, divided by square root of N. So what I did was I went ahead and put that my S was 200 right there. They just told us that the standard deviation in the sample was 200 hours. So I said 200 and then went ahead and solved for my standard error by saying 200 S divided by square root of 15 N gives me my standard error of 51.64. So there's our three-number summary. I went ahead and listed our alpha level as 0.025, so this time they specified, whereas before if they don't, just put 0.05 every single time. So then we're going to set up our hypothesis. So to set this up, just kind of the quick story of it without going into it, because the other video explains that, is that if I'm trying to exclude my sample mean, that 3882, from my null hypothesis. And first of all, I'm using mu here because I'm talking about an average amount. That's the population variable for a mean or an average. And I'm comparing it to 4,000 because that's what I'm trying to find out how my sample compares to the average life of all the bulbs that they tell us it's supposed to be of 4,000 hours. So I put 4,000 there, and if I want to exclude x bar from my null hypothesis, I'm going to say that mu is greater than or equal to 4,000 because x bar is less than 4,000. So to exclude it, I say it's greater than 4,000, leaves out that 3882, you're good to go. So that's how you set up your hypothesis. Then we have to decide if we're dealing with a z or a t test. In this situation here, because if you're doing it based on n in this case was less than 30. And if that's the case, you're going to use t. And in another situation where we're talking about do we know the population standard deviation or not, we have the standard deviation of the sample, but no information about the population. We assume we don't know it, so we're going to use t either way. So you can see how that works in one way or the other. So to solve for that, we're just using x bar minus mu, so just sample information minus population information, divided by the standard error. So in this case, it's x bar, which is 3882, minus mu, which is 4,000, the mu we're hypothesizing about, divided by the standard deviation, or sorry, the standard error that we just found over there, s divided by square root of n. And when you solve for all that, you're going to get a t value of negative 2.29. So from there, if you're using the t table instead of Excel, then you're going to try and at your degrees of freedom, which degrees of freedom is just n minus 1. So you would look at 14 degrees of freedom on your chart, try and find your 2.29. Don't worry about the negative, just try and find the absolute value of that number. You look for it, and you don't find 2.29, but you find at 2.15, the p-value is 0.025. At t is 2.624, you find the p-value is 0.01. So since the t falls between those, your p-value falls between these two p-values right here. So we don't know the exact p-value, but I do know it falls somewhere between 0.01 and 0.025. But if you're solving for it with Excel, based on the video from before where we're looking at the p-value chart to decide which Excel function we use, you go, okay, it's a t-test, it's a one-sided lower tail test. Thus, when you drill that down, you end up using this Excel function right here. T equals t.dist, TC, which is the negative 2.29 we calculated, DF, which is 14, and 1. Solve for that, you get 0.019 p-value. So under Excel, you can actually find the exact p-value of 0.019, whereas here we can only do a range, but you see that it checks out because 0.019 is between 0.01 and 0.025. So finally, compare your p-value to your alpha. You can see that the p is low right here. You know the rule, reject HO. And what do we say about that? What's like the analysis of the fact that we rejected HO? Well, we reject HO, so forget HO. We're saying HA. HA is saying that the average life of the light bulbs is less than 4,000. Well, if they're telling us it's supposed to be 4,000, and the manager is thinking, oh, well, maybe just the conditions of my factory, like something's going on to where it is actually not 4,000, it's something less than that, you can tell that we supported that because we're saying that it was less than 4,000, so the amount of hours was affected. So I know that's a mouthful. There's a lot of moving parts here and a lot of different situations that impact exactly how you go about this problem. Hold on to the very first part of the video with those 5 steps. That's kind of the general rules of thumb. Everything else pretty much explains the nuance between which situation you fall into. These 2 examples give you something to hold on to. So keep practicing, and I hope that helped out.